Welcome, dynamics students. This lecture will concern itself with work and kinetic energy for particles and mass centers. So far in this course, or any dynamics course you might be taking, hopefully you'll have covered concepts of particle kinematics, including motion in rectilinear coordinates, Cartesian, XYZ, IJK, unit vectors, polar or cylindrical, where you have an r theta z coordinate system and a tangent normal to any curve. That will be very important for relating our forces and accelerations. And hopefully you've also covered motion of a body, rigid or non-rigid, via motion of its mass center, provided it doesn't rotate. So with those firmly in mind, we're going to take one step further and start looking at energy and the nature of forces being conservative or non-conservative to give us another view into problems and give us another tool for solving them. In some cases, we'll be able to just literally use the energy considerations alone to solve for what we need. In other cases, we'll use an expression for energy conservation to give us that all-essential additional equation to get to an unknown we don't know, or to simplify our math if we end up with equations of motion in the form of a differential equation, which is kind of cumbersome to solve sometimes. So let's start with some fundamentals. This should be similar to what many of you have seen in your physics course, but we're gonna look at kinetic energy, a derivation for its expression solely based on vector algebra, which is something that's really a workhorse, pun intended, concept for dynamics and statics. So we're going to express the rate of work done on a body via a force application through its center of mass in terms of mass center kinetics. So again, this is, even though we're working on accelerating bodies and the work done to do so, because we were able to treat these bodies as points or particles at their center of mass, we're going to think of it like a particle. So we can start with Newton's second law, which is applicable for particles. So always good to start with Newton's second law, where we can say that the force resultant, or the sum of the forces, is equal to the mass of the body times the acceleration of its mass center of mass. So force and acceleration, of course, are both vector quantities. So we're going to go ahead and multiply both sides of the Newton's second law equation here by the velocity of the mass center, and we're going to use the dot product. So we're going to say velocity of the mass center dot force resultant is equal to the mass of the body times the acceleration dotted into the velocity of the center of mass. So another way of saying this is to say the velocity, the scalar velocity of the center of mass, or its speed, the magnitude of the velocity vector, in the direction that the force resultant is being applied, is equal to the mass times the acceleration of the mass center in the direction of its velocity. So we're looking at something where everything's parallel. We have the dot product. Kind of interesting if you're thinking about something maybe going around a circle at a constant velocity. Interesting to think these two may not be going in the same direction at all. So there are cases where this is zero, in which case we might not have to apply a force. So just thinking about this, the idea, not to go too far down that path, but just remembering that by invoking the dot product, we are specifically taking the portion of the velocity of the mass center that's parallel to the force resultant being applied, and we're taking the portion of the acceleration of the mass center that's parallel to the mass center velocity. So everything's got to be going the same direction. So now we're just going to do a little math gymnastics and rearrange the right-hand side, so that's this side, a little bit, and get an expression just in terms of velocity. We don't want to deal with acceleration at this point. So acceleration is just the first time derivative of velocity. So instead of a sub c, we have d v sub c dt, or v sub c dot. So now we have all expressions in terms of velocity. So we can use our principles of the derivative of a product and rewrite this term in terms of the derivative of the product here, and then throwing out a 1/2, so the derivative of basically v sub c squared is going to give us this expression up here. Basically v sub c squared. Taking the first time derivative, we would throw down a 2, we'd end up with v sub c, and then multiply that by v sub c dt, chain rule. So we've used the chain rule in reverse to go from this expression, we'll get a pencil here, to go from this expression here down to that one, which allows us to combine the two velocities with the dot product, and because something is definitely going in the same direction as itself, we end up with a scalar product where we have the full magnitude. We're going to pull the m over to back into the differential because we're going to compare the whole doggone thing to something else later. And the mass can come in and out if it's constant, which we're going to assume here. So, okay, so we end up with some math, gymnastics, and chain rule, and we have the time derivative of v sub c dotted into itself times the mass divided by 2. This should start looking familiar to those of you who remember the formula for kinetic energy. So using principles of dot product, something's parallel to itself, so we can v sub c dot v sub c full vectors is going to equal just the magnitude of v sub c squared, the whole thing. So we can replace that up here, and we can go back and remember, wait a minute, we've only been working with the right-hand side of this equation, but we now have an expression for that that's all scalar and all in terms of the velocity of the mass center. So now we're going to compare that back to the left-hand side. So the velocity of the mass center dotted into the force resultant, and remember dot product is commutative, so we change the order, is equal to the first time derivative of mass over 2 times the magnitude, just the magnitude, scalar magnitude, of the velocity mass center squared. Okay, so thinking about our units, force is in newtons, velocity is in meters per second. And so on this side we have power units. So, or you can think of Newton meters being energy per unit time coming from our velocity. So we've got, or joules per second. So this would be expressed in watts. This is power. And over here we have something that, if you can recognize from your physics, we've got a velocity squared times mass divided by 2. This is kinetic energy. And so we're looking at the time rate of change of kinetic energy, which is also going to be power, energy per unit time. So if we want to go from power to energy, we integrate with time. So we could integrate from some time of interest to another time of interest, or over a time interval we care about, over on the left-hand side, going down to here. And if we do that, if we do the integral, we're going to end up with force being applied over a distance. And for those of you who remember your physics, that's work. So the time-based integral of our force resultant dotted into the velocity of the center of mass is equal to the work done by that force resultant on the body's mass center over whatever distance it ends up traveling as a result. And again, of course, if we integrate this side, we just simply end up with what's inside the differential, which is our mass center, or excuse me, our mass of the body divided by 2 times the velocity at one time minus the velocity at the other time squared. So again, that is the change of kinetic energy. We don't have to know what all the velocities were in between those 2 times, and this is the fact that we have only the endpoints to worry about. The mass hasn't changed. If I know my velocity at the first time of interest and I know my velocity at the second time of interest, I don't have to care about what happened in between. So kinetic energy is a state variable basically in this case, because we only care about what happens at its endpoints. It's path independent basically. So that's a powerful tool if we're looking at solving a problem. We only have to know what happened at 2 time instants, and then we can basically know the cumulative work done by a force. And if we have some expression for velocity and we can get a force resultant from an FBD, we may be able to solve for some unknown in the problem that we don't know. So, okay, so what we've done is we've established a work-energy relationship. Work done by the total force resultant is going to equal the kinetic energy change of the body via the velocity change of its mass center. Okay, so let's look at two different ways we can do work. How many different ways can a force resultant change the velocity of a mass center? And of course it all ends up in the same place with a kinetic energy change or a frictional loss, as the case may be if we have non-conservative forces. But there's kind of two general categories of the way a force can be configured relative to the center of mass that does work, and that kind of simplifies our math and our thinking about a problem. So in the first one, we have a constant force that results in a mass center displacement. So the classic one here is gravity. Gravitational acceleration is definitely constant especially if you're near the surface of the Earth. If you're out in space, that's definitely not the case. But if you're, anywhere within a few hundred feet of the Earth's surface, where we typically work in engineering dynamics, acceleration is constant, your mass is constant, and so your force is constant. So you can take the force out of the integral, being a constant, and just look at your changes in mass center. And in that case, when you evaluate your integral, you're going to get two positions. So if you know the force and you know the starting and ending position, you know the work done, and you can calculate the kinetic energy change. So this is basically, if you know the force, it's not changing, you know your starting and ending position, you know the work done. Very convenient. The next type of force work done scenario is called a central force, and its unique characteristic is it has a line of action always passing through a fixed point. So something's tied down somewhere and is always acting from that point. Great place to set your origin of your coordinate system, maybe. And a magnitude dependent only on the distance r in this case, of the force's point of application to a fixed point on your body. So here's a little schematic of what that means. You've got your force always originating from the origin. Like the classic thing here is a spring tied down at one end. The spring is going to act only on its line of action, which you've tied down at some point P in the body. The spring's not going to pull sideways. It's only going to pull or push back and forth along its line of action. So we can use that line of action constrained relationship to simplify our math a little bit, and so we always know which way it's pointing. This is akin in a bit to a two-force member in statics, where you can have a compressive load or a tensile load, but if you know the orientation of a straight member, you know the direction of the force. So in this case, that direction could be changing with time. It is dynamics, but you know it's always along a line between those 2 points. So if we take that information on board and we look at writing an expression for velocity of our point of interest, our P here, our velocity P, if we look at it in terms of our kind of a polar coordinate system, the position of P would be R in the r hat direction. So the time derivative of that is d r r hat, our unit vector in the radial direction with respect to time, and of course that gives us the change in length with respect to time, r dot in the radial direction, plus whatever the radius is in the r hat dot direction, so in the direction in which that unit vector may be changing, which it could definitely change in direction if this is moving somewhere. Our radius could be changing. Okay, so we're going to say, because we know the force always acts in the radial direction with a certain function of distance, r, like the length that you stretch the spring perhaps, we can write an expression for force. So here's our F. We want r dot Fp, so we need an F. We got our P here, we need an F. So we're going to presume that the force is going to be a negative because we're thinking of springs, negative some function of r. So, the bigger r gets, the bigger f gets, or smaller, whatever. But it's always pointing in the r hat direction. Okay, we have a v, we have an f. Let's calculate f dot vp, because that's going to equal our kinetic energy change. This is the work done by this force. Okay, so here's f in its vector form, and we're going to dot it into vp. Okay, so we're going to foil it. So we're going to start with our function of a radius times, or in the direction, of our r hat vector, which is our force, dotted into our dot in that same direction. So something dotted into something go in the same direction. We take the whole magnitude of both. So we're going to end up with this, and we'll actually, because of the dot product, we'll end up dropping the unit vector. It'll just end up being this force function, and then our time rate of change of our radius. And then we're going to subtract because we've got a negative sign on the f, that's coming down here. We're going to look at our second term, where we have the function of the radius in the r hat direction times the radius times the time rate of change of the r hat direction. And if you remember from your cylindrical coordinates kinematics and your tan normal kinematics, a unit vector is always perpendicular to the rate of change of itself. So r hat and r hat dot are by definition perpendicular, which means the dot product is 0. So this whole second term goes bye-bye. And we just end up with that. So we can say that the rate of work being done, or the power being exerted by this force, is just going to be whatever that function of the radius the force has, which for spring is linear, times the velocity of point P, just times the magnitude. R dot is Vp relative to O. But if we want to know the work done by it, we just take the time derivative of that. So we integrate this term, that whole term. So time-based integral. So from one time to another, we've pulled this negative sign out in front of the integral, and we just have our whatever our function of the radius is, that is from our force, times r dot. We've decided to just note that it's in the r hat direction, even though technically that unit vector would disappear as a result of the dot product. We're going to integrate with respect to time, just to remind us, hey, all this was originally pointing in the r hat direction. And we get, in this case, we're going to express r dot as dr dt, means the same thing. We're integrating with respect to t. We can use our chain rule and get rid of the t's. And now instead of integrating from one time to another, we can integrate from one position to another, which might be easier to measure. Remember how we looked up with our gravity, we ended up with the work of the force done being position dependent. So we're gonna end up with another position dependent kind of expression down here. So we're going to end up being able to say that the work done by this central force, like a spring, is going to be the integral from the position at time 1 to the position at time 2 of whatever the function of radius or distance between the origin and our point of application are with respect to position. So that definitely should be looking familiar. If this were a spring, this F sub r would be replaced with K delta L, where delta L was the stretch, or the two positions of the endpoints of the spring at one time and another. So to simplify a little more and to relate to spring function, we're going to define some Greek letter function of r is equal to this integral. So we'll just say, whatever this function is, we're going to integrate it and get something else. So we can say, and then we can drop in our limits of integration. So we can say, because we've got a negative sign out here, we can say the work done by that central force is equal to this function, which is the integral of this, at its most distant time minus the negative of that same function evaluated at the position that the body would have at the first time. So it's just another way of saying complete the integral and drop in the limits of integration. Don't forget the negative sign. So now we've got work done by a force is now equal to the sum of some position dependent function. Just like with gravity it was linear, now it'll be a function of whatever our central force dependence is on distant. You know, you can think about things like, like gravitation. It's dependent on r squared. Spring is dependent on r. That'll be something that comes from your laws of physics, but now you know how to deal with it. So to give our obvious example of a spring, you could have point O and you got some spring and it's attached here at point P on this body that's moving around in space, and we can use our spring terms. If the spring's natural length is L0, that means it's not exerting any forces when it's that length, it's in equilibrium. Then our distance or our radius related function for this central force is the spring constant times whatever the radial length here is minus that neutral length. So this is r over here. So in this case our Greek squiggle letter as a function of r, which is going to be the integral of this with respect to r. We've already got an r, so we end up with a squared term, and we can define this as this position minus the neutral length is delta L. So we end up with the work of the spring being negative spring constant over 2 times our delta L at 2 different times, which is effectively at 2 different positions of the radius. So we have now rederived our familiar work or energy of a spring by treating it as a central force, a very basic central force, and also invoking our basic concept of a force dotted into the velocity of a body's center of mass. In this case, we didn't have to use the center of mass. We used the point of application of the spring. Okay. Next big concept. So far, everything we've worked with, work done by a force resultant is going to equal kinetic energy change of the body. Nothing's lost. We've also invoked the idea of a central force, which we'll get to, of a position-dependent energy, and which we can think of as a potential energy. Again, from physics, we're used to potential and kinetic energy. We can relate the work done by a force to a change in potential energy, which can then be equated to kinetic energy changes minus whatever we lose with friction. So let's think about friction for a second. So we have 2 types of forces when we're talking about work energy. Conservative forces, which are not path dependent and do not contribute to any kind of loss of total mechanical energy. And we have non-conservative forces, which are dependent on the path. So the longer a distance over which you apply them, typically the more energy you lose to them. Friction's a great example. Some of them are dependent on velocity. If you think about frictional loss to viscosity in a fluid, sometimes that can be velocity dependent. So when we're looking at totaling up all of our work done, kinetic energy changes, potential energy changes, that will only sum to 0 in an initial and final state if we haven't lost anything. So one of the easy ways to account for frictional losses or non-conservative force losses is just give them their own work and throw them into the tally. So in so doing, we can say, we can drop back. Let's make that link to work done to potential energy change. If we go back to that little Greek squiggle, which was the integral of our central force from one time to another. That's a position-dependent force, so is a linear force like gravity. So we can say all of our position-related forces, all of the work that they do, whether it's a constant force moving through a distance or a central force moving through a given radius with a given function, that's going to equal the change in kinetic energy of our body if we don't have any kind of non-conservative forces. So we can just equate those two as a work on this side, energy on this side. We have two different times. We can reshuffle it mathematically. So we have all the initial times on this side, all the final times on this side. And by getting all of the initial and final times on the same side of the equation, we can say, aha, the sum of the potential and kinetic energies are constant. So this is the mathematical derivation of our total mechanical energy conservation in the absence of these. So this is something most of you probably already know, but now we've really stepped through the math, starting with something really simple like the velocity of the center of mass dotted into the force resultant, looking at the definition of Newton's second law, the definition of the sum of the force resultant on acceleration and mass, stepping through some vector algebra and a little bit of math, looking at a couple of scenarios where work done by a force can result in a position change, and from that we now have derived an expression for total mechanical energy, potential and kinetic, shown that if we don't have any non-conservative forces, that sum is constant in time and position. That sum is constant. Okay, if you have non-conservative forces, then this isn't going to be constant, and you would simply say your initial state, initial energy, is going to equal your final sum plus work done by non-conservative. So we just throw them, I'll say work work done by non-conservative forces. So we just have to throw them into the tally and add up the work that they do and be sure we remember that whatever we started with, we're going to have to subtract the work of those non-conservative forces to get an expression for our ending state. So we basically have a very powerful third equation that we can add to maybe two equations of motion that we have and make our solutions simpler. So just to prove how powerful that simplification is, we're going to go back to our a previous example that we did in a prior lecture recording. We have our mass on a string that is being dropped from a given angle with respect to the horizontal. And someone wanted to know what the string tension was as a function of the angle to the horizontal. And to do that, we set up, of course, a coordinate system. We used polar coordinates. We drew an FBD of the mass center of the ball. We equated the force resultant in the radial direction to an expression for the acceleration in the radial direction in polar coordinates. And one-to-one applied Newton's second law. We did the same thing for the theta direction. Force result in the theta direction was equated to mass times the polar acceleration in the theta direction. But then we had to jump through some pretty interesting mathematics to perform an integral to get an expression for tension in terms of theta that was not a differential equation. It's really easy to come up with a differential expression falling right out of our Newton's second law. But we had to do a little bit of complicated mathematical solution to get an algebraic expression. So we're going to use our work energy expression to see if we can't liberate ourselves from the complex mathematics by giving ourselves a little bit different expression that might make the math easier to solve. Otherwise, the problem's exactly the same. So I've reproduced the schematic here, and I've started with giving an energy balance expression. We're going to start with the fact that we don't have any non-conservative forces, so we can just relate kinetic energy to changes to work done. So we're going to say that the change in kinetic energy of the ball is going to be equal to the work done by the only two forces that can operate on it, which are the string and gravity. So change in kinetic energy is going to be equal to the work done on the ball by the string, not the spring, although it's acting in the same way, plus the work done by gravity. So our kinetic energy expression, of course, at any time for the ball is the mass of the ball times the square of the velocity of its mass center. And we can use our good old polar coordinates to write a nice expression for that. Work done by the string of length L is 0 because there's no velocity change, or excuse me, there's no position change in the radial direction. The string stays the same length. So remember, work is force applied through a distance, or work dotted into VP, or excuse me, the velocity in that direction. I'm thinking of the point of application of our string, VP, or spring. Too many terms that sound the same. Excuse me. So if we don't have any velocity in the given direction in which the force is being applied, our V dot F is 0 and our work is 0. So another way of thinking about it is we applied a force, but we didn't move it through any distance. In this case, we're looking at the radial direction. The distance is not changing because the string connecting the ball to its pivot point is the same. So that goes away. So the only work being done is the work by gravity, which we can express as mg, the weight, times the vertical distance traveled, which we can get from the geometry of the problem. So let's use our polar coordinate system again to express the velocity of the center of mass in terms of r and theta. So we would say it's just using polar coordinates. We've got r dot in the r hat direction plus r theta dot in the theta direction. That's our standard expression for velocity in polar coordinates. We know that r doesn't change, so this term goes away. And we know that the radius in this case is our length r. So if we square this, and we just take the magnitude, we drop out our unit vector. Here's our square of the velocity of the center of mass. Look, it's only dependent on the angular velocity squared. So we're going to kind of keep that in our hip pocket to help us with the math later. And we're also going to get an expression for the vertical distance traveled, just using at any time. And so that's just going to simply be our y position at any time, L sine theta. That's our position at any time. Our initial position is when theta is equal to 30, so the vertical displacement is simply going to be our position whenever minus our starting position. So we end up with, since sine of 30 is 1/2, we can factor out the L, and here's our expression for vertical distance traveled. So if we say mg times vertical distance traveled is the work of gravity, we end up with this expression over here. So here's the work done by gravity for any theta, and that's equal to the kinetic energy change, which is 1/2 m times v squared. So we have a nice expression there. So let's take a look at the radial direction, the sum of the forces in the radial direction, because remember the point of this problem was to get a value for tension in the string as a function of theta position. So let's go back to our Newton's second law expression for the radial direction, because this energy balance expression is great, but there's no tension in there. There's no T, and we want an expression for T. So the only place to find T is in the radial direction. That's the only place. They just only pull in there. So let's go back to our Newton's second law. The sum of the forces in the radial direction is equal to mass times the acceleration in the radial direction. And we have this expression for acceleration in the radial direction. Now don't confuse this with our velocity expression up here. This is the first portion of a longer expression for total acceleration in polar coordinates. We've just taken the portion that's in the r hat direction. So from our ball FBD, our sum of the forces in the radial direction is the portion of gravity pulling downward, mg sine theta, minus the string tension. That's what we're looking for. So that's going to equal mass times the acceleration in the radial direction, which is what's in parentheses here. But because the string is not stretching or breaking, r double dot is 0, r dot 0, r double dot 0. So we just have this term left. And it comes down. And of course the value of r is L. So this comes down. We multiply by an m. ma in the radial direction equals the sum of the forces. And we're kind of back to where we were the first time we worked this problem with, well, that's nice, but now I again have a differential equation. I have this velocity squared that I don't know a way to evaluate. Now we go back to our energy expression. We just so happened to get an expression that included the square of the angular velocity being equal to other things that are algebraic expressions of our theta. How handy. So we can just factor out the portions we don't want and get an expression in this case for L, M, and theta dot squared in terms of G and sine theta from our work energy expression here. And substitute that right down here, and my marker didn't work coming down here for this. So that's what we can see here. So we're substituting for this term from our work energy expression on the other page. So we've got that written out here. So work energy gave us ml theta dot squared equaling 2mg sine theta minus 1/2. So this was from work energy. So we can just substitute into here in our Newton's second law expression, which gives us tension, and all of that goes there. And without having to do the complicated integration trick, which was totally valid, but without having to do any kind of more complicated math, we're able to get an expression for tension, an algebraic expression in terms of sine theta. And when we simplify, we find we have the same expression that we got when we did the mathematical manipulation of just the equations of motion that fell out of our Newton's second law. So work energy gave us a math alternative, and it did give us a third valid equation that simplified things. We didn't have to use that third equation to solve for like another unknown that we didn't know this time, but we did use it to simplify the math. So now we've found two ways to work the same problem. Okay, we're going to do one more example that's a little bit new, where we bring in a spring, so we can look at both the constant force type of work, our work done by force type 1 and 2. We have one of these central forces in the form of our spring. So in this case, we've got a mass block sliding down a ramp, and we're expressing it as a block to just emphasize the fact that we can have friction operating on this bottom side, and in fact we're given a coefficient of kinetic friction of 0.3. So our total mechanical energy at our initial state and our final state is not going to be the same. It's going to be initial is going to equal final plus whatever work is done by that friction, which means we're going to have to know how far something traveled, and we're going to have to know the magnitude of the frictional force, and hope it doesn't change with position or time. So we've got an initial velocity in this case. So think initial velocity, initial kinetic energy. And we've got a spring constant. We're indexing to the neutral length. So the mass will slide down 10 inches. It'll change its position in the down ramp direction by 10 inches before it even contacts the spring. Then the spring's going to start doing work on the mass as it continues down the ramp until we've reached a point of force balance and zero velocity, hint, zero kinetic energy. So we've been given this problem in old-fashioned British units, so we also need to remember that our weight of 25 pounds, when we use gravitational acceleration, the British system will give us a block mass of 0.777 slugs. So if we ever need to do F equals ma, remember our m in the British system is a slug. So we know how many to add or multiply, and we're given a spring constant. And we're given gravitational acceleration in inches, so you can convert that to your familiar feet per second squared if you want to verify. Okay, so time equals 0, the block's motion is as shown in the figure. We've got a known position and we've got an initial velocity. And somebody wants to know what the max force we're going to end up with in the spring when the block finally comes to rest. So we're going to invoke work energy first. Initial mechanical equals final mechanical plus frictional work. And we're going to think about a few other things we're going to want to do. We're going to define the max spring compression distance. So we're going to define a delta L that corresponds to when the spring is compressed as it's going to get. And we're going to remember that, hey, at that point the block's not moving. So that gives us another zero kinetic energy relationship. We can notice that the block has to travel 10 inches before it even starts to compress the spring, and then its distance of travel to the point of maximum spring compression will be that delta L. So the total distance traveled is 10 inches plus delta L, and that's going to be the distance over which the frictional work is done, which will help give us a way to calculate that. And we have a theta angle for the block, which we're given as 36.87 degrees. So that'll help us calculate the work done by gravity or change in gravitational potential energy, if you will, as well as helping us calculate any distances. Okay, we're going to approximate. Having looked at the block as a big square to visualize frictional forces, now we're going to go back and invoke the fact that nothing's rotating, the block's not rotating, so we can treat it as a particle at its center of mass. So it's going to kind of just be a positional dot here forward, other than in the FBD. So we're going to treat the whole thing as that point, the center of mass. So even though this is work energy, we do not skip our FBD and our coordinate system. And I'll go back to the schematic, not showing the coordinate system, but just thinking about it, I think it would make a lot of sense to maybe have an X coordinate system that is maybe increasing in this direction down slope, and a Y perpendicular to it. The other way would be to orient where you've got your vertical up and down, because that's where we're going to be changing gravitational potential energy, but most of the action is happening up and down slope. So an XY like this may make some sense. So let's see what we ended up doing. So we jump down to the FBD. We've got gravity downwards, 25 pounds, normal force perpendicular to the ramp. Since we're going to be compressing the spring, if we are compressing the spring, it's going to be pushing back up, and because we are moving down ramp the entire time, the spring doesn't push us back up. Frictional force is consistently operating up ramp. So we could do a perpendicular to the ramp, down the ramp, force tally, and then look at our accelerations in both directions. So starting with normal to the ramp, We can simplify our lives and give ourselves an expression for friction by noticing that the block is not moving normal to the ramp. So the sum of the forces in the perpendicular to the ramp direction are actually zero. So there's no acceleration up out of the ramp or down into the ramp. So we can equate that force sum to zero. Statics problem in the normal to the ramp direction. So that gives us mg cosine theta equaling the normal force. We know the weight, we know theta, so normal force ends up being 20 pounds. That gives us our frictional force. So now we have an expression for friction, 6 pounds. And so we know if we can find out how far the spring compresses, we now have an expression for the total work done by the frictional force. So other important things, we can calculate an initial kinetic energy, 1/2 times mass times the initial velocity squared. We know the final is 0. We know our initial gravitational potential potential energy. We're going to reference to the lowest position. So we have a positive potential energy at our initial point. We're saying our final height is 0. So we can use trigonometry and say our hypotenuse is 10 inches plus delta L, and then sine theta is our height portion. So our total potential energy is effectively the work that gravity would do to raise us to that point. So we have mg times the height here. Sine theta times 10 inches plus delta L is the height. And again, work done by frictional forces is 6 pounds times 10 inches plus delta L. So we got a lot of expressions floating around here. And we got one big unknown here that we keep seeing again and again. So we'll definitely end up solving for delta L somewhere. We have one more expression that we can write. We've got our central force in terms of the spring. Its initial energy is 0, and its final energy is 1/2 K times its compression delta L squared. So we can invoke energy balance now directly and say initial kinetic energy plus initial potential energy plus initial compression, potential energy, initial kinetic plus initial potential gravitational plus initial spring potential, which will be 0, is going to equal final kinetic, which will be 0, final potential from gravity, 0, final potential from the spring, whatever determined by delta L, plus whatever work was done by friction. So we can write some expressions just to show that, which we have here. Initial kinetic energy, 1/2 m initial velocity squared, and the arrows just report what the value of the product is here. And we have the potential energy from gravity split up into 2 to make our math easier, because we're going to be solving for delta L. So we have part of the gravitational potential energy of the height given to us by the 10 inches. That gives us 150 inch-pounds. And then we have a little bit more height here that the gravitational force works through for whatever height we lose as we travel down that delta L. So both of these expressions are portions of our gravitational potential energy. So everything I've just circled, the sum of those, the 29 and change inch-pounds, 150 inch-pounds, and then delta L times 15 pounds, that's our initial total mechanical energy. So that's going to end up being our final spring potential energy, which we have our spring constant and we have our delta L squared, plus whatever work is done by friction. We're going to lose that. And we're breaking friction up the same way we did gravitational potential energy change. We're saying, okay, we know the work of friction over that 10 inches is just 6 pounds times 10 inches. And the work done by friction on the block as it's sliding down and compressing the spring is going to be 6 pounds times the distance of spring compression delta L. So now we have terms that we have a number for, and we have terms that just have a delta L. One equation, one unknown. It ends up being a simple quadratic equation in delta L, which we need to solve for, which we can do easily with the quadratic formula. So we get a delta L of 1.635 inches, springs compressing. And so we can use our expression for spring force being equal to K times delta L, and we get 164 pounds. We can get everything else we wanted to know about the problem from that too. So we ended up with one equation and one known. So we didn't really have to go back to the equations. Well, we used an equation of equilibrium, but we didn't have to invoke Newton's second law as directly as we did in the previous problem. So we used work energy basically to solve for what we needed to know in this. It was a little bit simpler and more amenable to that. So we didn't end up having to actually do anything with Newton's second law the way we did in the former problem. But it's useful in both cases. So that is it for this lecture. We will pick up the next one and have some more examples of some curvilinear motion, where we're going to apply work energy to help us find what we need to know in those curvier situations.